This question is titled, What can and cannot be easily done with regular expressions? And I want to talk a little bit about the theory of regular languages, and I want to tie it to what a regular expression really is. When we talk about regular languages, this is the starting point for a longer discussion on things like custom parsers. But we usually talk about this in terms of a grammar, where a grammar is some set of symbols, some starting point, some stopping point, and some rules. Generally, when we talk about grammars from a computer science perspective, we're talking about this from a generative perspective. We're talking about production rules, which allow you to exhaustively create the entire possibility of everything that would fit within that language. And I'll show you an example of what that might look like for a very simple language. Here is a very simple language where everything is a sentence, and you have symbols: sentence, verb phrase, adjective, noun, I bought a, fast, slow, car, truck. The terminal symbols, the symbols which you can't further produce productions on, are I bought a, fast, slow, car, and truck. And the rules are, you take a sentence and you break it down into a verb phrase and a noun phrase. The verb phrase, you break it down into I bought a. It's the only choice. The noun phrase, you break it down into an adjective and a noun. The adjective can either be fast or slow. The noun can be car or truck. And you can think the entirety of this language is I bought a fast car, I bought a slow car, I bought a fast truck, I bought a slow truck. What you can think is the language is formulated in terms of the rules which then exhaustively create this language. Well, this may not seem altogether that useful, but it ties in very closely to how regular expressions are actually constructed. What you can think is this could also be used in order to determine matches. And if you look at this, you're going to see it's kind of like a graph, like it's saying, oh, at this point you can go here or you can go here. It's kind of like a graph that you might do some sort of breadth first search on to find all the possibilities. Well, when we talk about regular grammars from a computer science perspective, we're talking about grammars which have a restriction on their rules. You can have a non-terminal symbol that turns into nothing, a non-terminal symbol that turns into a terminal symbol, a non-terminal symbol that turns into a terminal or a non-terminal symbol. And this creates a certain class of languages which can be solved by finite automata. Here is a simple example of a regular language. And here are some terms that you can get from that regular language. You can take the S and give the start symbol and produce nothing. You can take the start symbol and produce just a single terminating symbol. You can take the start symbol and produce a terminating symbol and another start symbol. And you can take this thing and then produce an empty string, so you can get the same T again. You can take this thing and replace it with the T, and you can get this thing again. You can think this language is basically any number of that T terminating symbol repeated. That's the entirety of this language. A finite automata, we can prove, can match against this. So any pattern that we create that's just one or more of a repeating symbol can be matched against with a finite automata. Well, it turns out that we can actually view this as a graph. And we can look at a more complex language like this. A start symbol, a terminating symbol. The edges indicate the character that you match against, and some nodes in between, A, B, and C. So this is a language which goes from the start symbol back to the start symbol with an A or a B, then from the start symbol to the A, capital A, with a single A, from the capital A to the B with a single A, with the capital B to a C with a single A, and then to the terminating symbol with an A. So this matches any number of B's, any number of A's, followed by 4 A's. And this may very likely be not too far from the actual regular expression state machine that's created when you try and match any number of A's, any number of B's followed strictly by 4 A's. It really is just a state machine that looks like this. This is about as far as the correspondence between regular grammars and finite automata really get to the regular expressions that we use. Because it turns out that when we talk about regular grammars, we're talking about a hierarchy of these language rules. Regular grammars, context-free grammars, context-sensitive grammars, and unrestricted grammars. And certain patterns that we can search for can be expressed in regular grammars. Certain patterns we can search for cannot be expressed in that fashion. Things like HTML and XML are context-free. But the regular expressions that we use day to day aren't really regular grammars because they have backtracking and they have some of these things like these look-behind references. In other words, when you start to think about where regular expressions are used, can be used and can't be used, you will find that there's a class of things that you simply cannot match. An A, 3 A's followed by 4 A's, you can match. 4 A's, 4 B's, you can match, no doubt. Any number of A's and then the same number of B's, You cannot easily match. In Python, I don't know that there's a way to do this where you match 3 A's and then 3 B's, 2 A's and then 2 B's, but not 2 A's and 3 B's. Because if you do this, this matches any number of A's and any number of B's, or this matches an A, B, A, B, but to match them side by side isn't really possible. And the reason for that is this is a context-free grammar. However, if you were to use another module, a PCRE module for Perl-compatible regular expressions, there are extensions to regular expressions like these, sub-pattern matches, which do allow you to match some context-free grammars. And there are things like back references that we've seen that do allow you to match context-free grammars. So I want to boil it down to you like this. When you're constructing regular expressions, it is valuable to be broadly aware of what constitutes a context-free grammar versus a regular grammar, because that will largely hint for you where the regular expression is just going to hit a brick wall and you won't be able to get any further. In general, the distinction between these is specified in terms of the production rules. And this is a little bit more research for you to do to really understand how these work. But it really comes down to how the rules are produced and how one symbol can turn into another symbol. Largely, for the actual regular expressions you use, they're not really regular grammars, so there are often ways for you to get around this theoretical limitation using things like back references or backtracking, or back references or sub-pattern matches or things like that. In general, once you start trying to match things which are context-free, like programming languages or HTML or XML, in general, you don't really need to prove that that's a context-free grammar because you'll go to the HTML webpage or the XML webpage, you'll go into Stack Overflow, this is context-free, and some people say yes, and it'll be a big hint that the regular expression, while it might be possible, is generally a bad idea. Do try to use regular expressions instead of ad hoc Python code for matching things, as long as those things that you're matching are largely regular grammars, or largely have simple production rules, largely just kind of expand on one side. And when you look at the rules in a little bit more depth, you'll see. Try not to use regular expressions to match things like HTML or XML. You're going to do it anyway because you got to do it in a pinch. And what does egrep give you other than a regular expression? But understand that there is this formal distinction between these grammars that does create a hard brick wall past which you may discover that a regular expression is completely and utterly incapable of solving your problem. And the most immediate place you'll see that is parsing anything that's context-free, which generally almost all programming languages are context-free grammars. Almost all markup languages are some form of context-free grammar. HTML, XML, these are context-free grammars. JSON is context-free as well. And so generally, if you're trying to use regular expressions to parse JSON, HTML, XML, or a programming language, do it as an ad hoc thing in small pieces, but don't do it in lieu of writing a full parser or writing some custom code, because you will almost certainly inevitably hit a brick wall, or you'll hit something where the regular expression you have to write is truly horrific.